Oh, hello. Fancy seeing you here. You must be here for trigonometric equations. Well, so am I. And today, we're going to look at trig equations with multiple functions. So here we're going to have trig equations like this, where it's not just based on sine x, and it's not just based on cos x. We've got both of them involved here. And this could potentially be a bit tricky. It's going to challenge how we think and how we approach these kinds of scenarios. Generally speaking, we're going to want to make sure we can find a way to get a single trig function in an equation instead of having multiple. So that might involve factoring, if that's possible, or potentially using identities, all depending on what we can do in any given situation. There are 7 examples for us, which is quite a few, and we're just going to go through every single one of them. And of course, I'll encourage you to try them once you see a couple, or if you want to try them now, feel free. Anyways, factoring can be used to solve this particular equation. I know what you're thinking. Factoring what? There's nothing common on this side. There's nothing common on this side. What's the old thide talking about? Here's the magic that we're going to undergo. I'm going to take this and transfer it to the other side, so that instead of this equation, I'll have a manipulation of it. So sine x cos x minus 2 cos x equals 0. And now I can see that it's possible to factor. I can factor out a common cos x from each term. Therefore, I can write this as cos x times sine x minus 2. And we know from however many times we've done in our lives, when we have a product that is equal to 0, either of the factors could equal 0. So either cos x equals 0 or sine x minus 2 equals 0. In some other cases, we've noted that this particular line isn't so much necessary. All we really need to establish is that sine x is equal to 2. So it's understood that we can immediately get that from this factor. Of course, if sine x is equal to 2, this will have no solution. And then cos of x being 0 means that x can be something. And according to my knowledge of trig, that happens at pi over 2 and 3 pi over 2. Final check here is that these are our solutions from 0 to 2 pi in radians. We were asked for this, from 0 to 2 pi in radians, so we are good. Just for funsies, I might just state my final answer once again. You can state it as x equals this stuff, or you can go with that element of formality that I've been playing with in other lessons. But either is okay. Whoa. So there's the final answer. So that's one where we're solving by factoring. There could be other cases where factoring is not really an option. So we're going to have to use identities. Ooh. So an equation like this is not quite as direct. But let's see what we can do. I see there are some like terms swimming about. This cos x and the 6 cos x. Those are like terms. I can just add cos x to both sides. So then I'll have 5 sine x equals negative 5 cos x. So we've still got multiple trig functions here. But I know that there's a relationship between sine x and cos x. In fact, the ratio between them is tan of x. So if I take this and I divide by cos x on both sides, on the right side, that's just negative 5. Now on the left side, we've got 5, and then sine x divided by cos x is tan x. Next step would be just dividing both sides by 5, which would allow me to say that tan of x is -1. We can establish that the reference angle for that would be 45 degrees. And then dealing with quadrants 2 and 4, because of the negative ratio for tan, we can finish off by saying x has to be either 135 degrees or quadrant 4, 315 degrees. And we were just from 0 to 360. We don't have to worry about coterminal angles or anything. This one is done. So those ones were a bit more direct. When it comes to using identities, we've seen that there are tons and tons and tons of ways to actually create equivalent statements. So there's always multiple ways that an identity can branch out. There's always equivalent statements. So we're going to have to play with the options that are available. Generally speaking, you want to find connections between what you have and what you want and see where that can go. Like with cos of 2 theta, there are multiple ways to express that. You can express cos 2 theta as cos squared theta minus sine squared theta. You could also say that it's 2 cos squared theta minus 1, or you can also say that it's 1 minus 2 sine squared theta. There's at least 3 ways to replace that. And then of course we can even consider what we can do with secondary trig functions and manipulations of those. So how do we pick and choose? Well, if I'm looking at this, I notice I've got cos theta over here. So it'd probably be most ideal if I could actually keep this in terms of just cos theta, right? Why would I introduce sine if there's no sine in there to begin with? So I'll keep things in terms of one trig function as much as I can. Whoa. Feel free to try this. In fact, feel free to try the remaining 5 examples and see what you can do. And see if they match with whatever I do. So I'm going to choose to express cos of 2 theta as 2 cos squared theta minus 1. And then my right-hand side is just cos theta. What can I do? We've got a second degree trig equation. Ideally, this is factorable, and it says non-calculator, so realistically, it probably should be. So I'll just get everything to one side, and I'll go from there. There's going to be 1 involved. And I probably want to subtract. There we go. So from here, my 2 cases are that cos theta could be -1/2, or cos theta could be 1. Where do each of these go? This one might tell me that theta would be, I don't know, reference angle would be pi over 3. So in quadrant 2, we've got that. And in quadrant 3, whoa, color change out of nowhere. Quadrant 3, we've got that. And this one, where is cosine theta equal to 1? That is right at the beginning. So that's 0 by. What domain are we doing this over? Ooh, all reals. So we need a general solution here. So we could have this first angle and everything coterminal with it. We could have the second angle and everything coterminal with it. And then this last angle, which is 0, and everything coterminal to it, but 0 plus anything is just that other thing. So let's just make sure this is completely simplified, and we just write the 2k pi part. And that, of course, is as long as k is an integer. And that's that. Again, see if you can try all these other ones. This next one does ask us for multiple methods. So see what you can do. See if you can find multiple ways to solve this one. And I'll show you what I come up with. Hopefully you paused and you're resuming now. 3 cos squared x equals sine squared x. Neat. First thing I see is the potential to just divide by, not cos, or not sine. I was going to divide by sine. Silly me. But anyways, potential to divide by cos squared x, and that's very similar to that first identities one we looked at on the first page, that second example overall, where we said, well, there's a ratio between sine and cosine, it's called tangent. And that's what I get there. And that means that 10x could be root 3, or 10x is negative root 3. That is part of the pi over 3 family for both cases. And positive or negative, we're just getting all 4 quadrants. So then x could be anything in the pi over 3 family. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. How far are we going? Just up to 2 pi. So that is done. That's one method. There's another way to go about doing this, though, because we do have a way to relate sine and cosine when they are both squared. So we've got that 3 cos squared of x is equal to sine squared of x. But I could write sine squared of x in terms of cosine. In fact, I could say that it is 1 minus cos squared x. In which case I've got that 4 cos squared x is equal to 1. I've got that cos squared x is equal to a quarter, which means that cos of x is either 1/2 or it's negative 1/2. And again, just like in the other method, that means we've got a reference angle of pi over 3. This one says deal with quadrants 1 and 4. This one says deal with quadrants 2 and 3. So all 4 quadrants, giving us this final answer. Not 3 pi. What am I doing? There we go. So no matter what, we get the same answer. And there is even another way to do this. You could probably express cos squared in terms of sine squared. We write it as 1 minus sine squared, and boom, you've got another way. So we've got options. You know, generally speaking, I've been making sure things get into terms of a primary trig function. For me, that's just how I'm used to them. I prefer to read trig equations with primary trig functions. It's very possible to solve them with secondary ones instead, if you are okay with playing with secondary ratios, especially for special angles. But that's up to you. In any case, I think there's 3 examples left now. Hopefully you've been trying them all, or if you haven't tried this one yet, quick, do it, there's no time. I only see one potential option for me here. I've got a cosine, and I know I can express sine squared in terms of cosine, so I'm going to do that. Okay. Oops. I've got a second degree one now, so I'll just move everything the same side. And 3 minus 2 is when? Non-calculator, I hope this is factorable. Well, it's got to be a plus. What am I doing? Boom. So 2 scenarios. One is that cosine of x is negative a half, or cosine of x is negative 1. What's that going to give me for answers? Negative 1/2 means that we are in the pi over 3 family. So looking at quadrants 2 and 3, we've got that and that. And again, that's just from that. And then we have one answer that comes from this. Cos of x is negative 1 when x is pi. So that's how everything contributed to this final answer. Whew. Hey, this next one has a secondary trig function. Well, that's all sorts of exciting. All right, I've got options. I might just rewrite it as a primary, because I've been dealing with primary trig functions this whole time. That probably makes the most sense. 3 plus 3 over cos x. In which case, since this is over cos x, now I'm thinking to myself, this could be written as something over cos x, so I'm going to do that. Nice. And in fact, I could just multiply everything by cos x. So I'll multiply this by cos x, I'll multiply this by cos x, I'll multiply this by cos x. Get rid of that fraction-y fraction, and now I've got that 3 cos x plus 3 is equal to 2 sine squared x. Wait a second! That's what I had up here. What a ploy, what a ruse, what a gambit. So that equation that we have down there looks exactly the same as this business here. Wow. That's pretty wicked. Let's continue with this. It'd be the exact same solution. I could copy and paste, but then you wouldn't get the entertainment of watching me write. And this factored. This gave us possible solutions. And then we got answers out of that. Equals, x can't equal a set element of, there we go. And again, that was pi over 3 family, but where cos is negative, so quadrant 2 and quadrant 3. Boop. And then cos of x is negative 1 when when x is pi. Only thing to potentially watch out for here is possible existence of non-permissible values, just because secant of x has non-permissible values, and it's essentially wherever cosine of x is equal to 0. Because as we can see, if cosine of x is equal to 0, then we are dividing by 0, and that would be bad. And similarly here, if cos of x is equal to 0, that means we're dividing by 0. That would be bad. Fortunately, we don't have any solutions where cos of x is equal to 0. We have a solution where cos of x is negative a half and cos of x is negative 1. But not where cos of x is equal to 0, so we don't have to worry about that at all. Well, let's try this last one. Ooh, we're just flying. Oh my goodness. Well, that's all sorts of exciting, I guess. What could we do? Hopefully you've explored this, you've tried it, seen what options you have available. I'm thinking to myself, I'd rather this was in terms of primary trig functions. And in fact, so like, yeah, I can change the secant x and cotangent x. I might rewrite tan x as well. So 2 secant x is 2 over cos x. Tan of x is sine x over cos x. And cotangent of x is cos of x over sine of x. Whew. At some point in my life, I am probably going to want a common denominator. Yikes. Okay. So, I'll rewrite that left side as 2 sine x over cos x sine x. Just because I know that those are going to have to both be in the denominator. Which means that this term can be rewritten as sine squared x over cos x sine x. And this other one can be written as cos squared x over cos x sine x. So if I multiply everything by that denominator, I just get that 2 sine x is sine squared x plus cos squared x, which means that 2 sine x is equal to just 1. So sine of x is equal to 1/2. Neat. This gives us a reference angle of 30 degrees, which is pi over 6. We're in quadrants 1 and 2. So in quadrant 1, we're that. And in quadrant 2, we are that. Once again, just be aware of the potential for restrictions. We do not want cosine of x to be 0. We do not want sine of x to be 0. And that hasn't happened here. Essentially, any multiple of pi over 2 would be an issue for us. Because, where am I at? 0 or pi or 2 pi would all make sine of x equal to 0. And then pi over 2 and 3 pi over 2 would make cos x equal to 0. Which would be unideal. But that's not what we got. We got that sine x was 1/2. That is part of a special triangle, so neither sine nor cosine of that are equal to 0. So this is good to go. There is some practice. Ooh, quite a lot. It's not a massive ton, but it should be enough for you to just get a feel for solving when you have to use factoring or identities, essentially multi-function equations. But that is the end of this whole entire topic. Try out the questions from the 2019 Provincial, try out the textbook review, and of course, always let me know if you have questions, comments, concerns. Just reach out via Teams or see me in class, because that's also an option. I will see you in the future. Tell everyone I said hello. Goodbye.